Okay. If you want to get closer, you can get closer. Not very far. Okay, so last time we have been we worked on the statistics of the speckle, if you remember. I hope you got a chance to review the last week course. We didn't finish, so I want to continue on that. But today is going to be really relaxed. I mean, you can relax today. It's going to be more about experiments and some beautiful results. So, I mean, if you want to get closer, you can push closer to the screen. So we built statistical tool to describe the speckle this week, if you remember. I'm going to review rapidly the main results, okay? And I want to introduce you to the field of mesoscopic optics, where you are going to see that these statistics does not apply in all cases, and actually when the scattering is very strong, the hypothesis that we made will not be valid anymore, and that starts to be interesting in terms of new physics. Okay, so let me put back, maybe I put directly, let's see. So that was last week course, if you remember. So I described the speckle pattern, if you remember, and the main idea was that the speckle pattern is a direct result of the wave nature of light. Okay, this is an interference process where the bright spots are constructive interference and the dark spots are destructive interference. Okay, so this is something that you cannot obtain from transport theory, from diffusion approximation. I mean, this is not. It doesn't come into that picture. You have to go a step further, and that's the reason why I introduced the statistical approach to describe the speckle pattern. So you remember that's the speckle pattern, that's the diffusive light. So when you mix many speckle patterns, you may reach this type of picture, but they are fundamentally different. Okay. So let me skip to where we stopped last time. How do I do that? Let's see a summary of the main results. There we go. Okay. So if you remember well, we said that yes, get closer. It's today's for us to be close and to watch the movie I'm going to show you. So you remember that to obtain this type of image, this is the result of a sum of many complex numbers. We call them phasors. Okay, so it's a sum of phasors here, defined as a sum of complex number with amplitude and phase alpha k, phi k. Okay, and the total. So those complex number here correspond to different trajectories through the scattering medium. You remember? So at one point when you make a measurement, you measure the interference between all possible trajectories through the scattering medium, okay? And this results in a new field that can be constructive or destructive depending on the sum of these phasors, okay? So assuming this, okay, so that's the main result for the statistics of speckle patterns. So this is very general actually, not only for disordered system, but also for scattering on surface or any type of speckle. So from there, actually we use this approach here to compare to measurement. So what you can measure first is the probability distribution of the amplitude, or the probability distribution of the intensity, for instance. Okay. That's not the one I wanted to show you. No, this one is not complete. here. Okay, so distribution of the amplitude of the intensity. This is something you can measure directly, and you can compare with your model. Okay, if the model works, we should be able to fit the data. Okay, so typically here, for instance, for the intensity, probability density of the intensity, you have an exponential decay. This is a semi-log scale representation. So this straight line actually is an exponential decay, right? And you see it's a straight line, so it's really described by this function here, which is the exponential, decaying exponential, okay, which comes directly from this model, okay. So this model perfectly describes the probability density of the intensity of the field here. The field itself, A, so the amplitude itself has a slightly different distribution. If you remember, this is called the Rayleigh distribution. It starts from 0 and then go up and down, okay? Same thing that can be described directly by the model that we have, okay? And then we define the contrast of the speckle pattern, okay? Which tells you that, again, there is a mistake here. So this is the square root of the variance of the intensity over its average is 1, okay? And then we define two very important quantities, which are the correlation function of the field, so it's called the field-field correlation function, and the intensity correlation function, okay? So the idea is you look at your speckle, okay, and you change some parameter. It can be the frequency, it can be the configuration, it can be the position, okay? So by a slight change, you want to see how much the two pictures of the speckle pattern are correlated, okay? And you increase this difference between the two images, and you see how much how fast you decorrelate the speckle, okay? So for instance, if I change frequency, if I compare my speckle at one frequency and at frequency plus delta nu, okay, so CE of delta nu, so I compare the field at frequency nu with the field at frequency nu plus delta nu. I average over configurations here, over ensemble average, okay, and that tells me how much they are correlated, okay. So there will be some value of delta nu, after which I get 0 here, meaning that I'm completely decorrelated, okay. That's for the field. You can define the same thing for the intensity. So here the intensity is centered, I minus I average times I of nu plus delta nu minus I of nu average, okay? So this is the definition for the intensity. And there was a very nice correlation that we demonstrated last time, which is called the Sigurd correlation here, which tells you that the correlation of the intensity is equal to the modulus square of the correlation of the field. Okay? So this is something that we demonstrate based on this model here. Okay, assuming that we have statistical independence between amplitude and phase. Okay, that tells you that there is a direct correlation between the correlation of the intensity and the field. A very simple relation. Actually, one is the square of the other. Okay. So what does it tell you? It tells you actually that all speckle spots are independent from each other. Okay. There is no long-range correlation. So one speckle spot can increase, decrease independently of another speckle spot. They live independently. Okay. So if you average over many configurations or many frequencies, okay, what you find is that the speckle will self-average, okay? If there is no correlation between different spots, you will have a self-averaging effect of the speckle pattern, and you get something which should be smooth at the end, okay? Whatever the parameter that you are changing. Okay, I will show you the effect of self-averaging and the limit of this effect, okay? But so if we are in those conditions, if we have a complex Gaussian random variable, all these results are fulfilled, okay? the expression for the distribution, the Siegert correlation, linking the field correlation to the intensity correlation, and the fact that the speckled spots are statistically independent and they self-average over any variation like configuration or frequency. Okay. You understand this concept of statistical independence? The opposite will be if the speckle pattern in this image were statistically dependent. It means that if one speckled spot increases in intensity, another one will also increase in intensity. That's correlation. Okay. Here they change completely randomly. Okay. They don't have any connection between them. So if you vary the system, at some point you will completely self-average this picture. Okay. Any question on this quick review? Question? No? Okay, so let's move to what is called mesoscopic optics. Okay. I put in the presentation, I put some reference from Azigenak, my colleague from New York, from Queen's College, who has done a lot of work on this topic. So that's actually a book chapter, and he has many papers, but that's a good review here. So you see the titles, waves in random media, okay, and here wave propagation and localization via quasi-normal modes and transmission against. So this is really all the physics that is behind this system, and I will describe to you the experiment. So this experiment was developed by Azigenak at Queen's College, and we are working on a similar experiment. Actually, CD is working on this experiment. So here you see the configuration at Queen's College, which is slightly different. Okay, and I really want to go into that experiment and show you results, measurements of the speckled pattern, and what we can do with that. Okay, so this is a very smart experiment if you want to do statistics. The idea is to have a tube, so it's a copper tube. You see it here. Okay, so this tube is just reflective for microwaves. We are going to work in the microwave range. Okay, and this tube is filled with scatterers. Okay, so in that case, I will show you we are working with polystyrene balls. Okay, and so we have you can see on the picture here we have a source here that emits microwaves on one end of the tube, and on the other hand we have a detection here that I will describe in more detail that measure the transmitted light or microwave. Microwave is also electromagnetic waves, but at larger wavelength. Okay, so we are talking about centimeter waves. So we are measuring here on the output the field. So how do we do that? So let me describe to you in more detail the sample itself. So you see here the end of the sample. Okay, so it is filled with these small balls. They have like typically a centimeter diameter. Okay, you see there are many balls like that. They have an index of refraction of 1.4. So compared to air, that means that we have scatterers for electromagnetic waves. Okay, a quite high filling fraction, 52%. Okay, all that in the copper tube that you see the end here, with a diameter of 7.5 centimeter and a length of 1 meter. Okay, all the material that you see around here is actually to isolate from radiation. Okay, so those are very strong absorbers to avoid reflection in the room and all that. Okay. So to measure the microwaves, we use a very simple type of antenna. So you see it here. So we use a semi-rigid coax cable like that, which is made of a central wire and an outer wire, okay? And simply by bending the central wire, like you see here on this picture here, by bending this wire, actually you create a detector, okay, which acts like a dipole, okay? So it's going to measure the field oscillation in that direction, okay? So very simple instrumentation in that case, okay? You have the scales here in centimeters, okay, and this antenna is brought close to the, so there is like a plastic cover here to block the balls inside the copper tube, so you can see it in reflection. So we get very close to the output of the sample, and this antenna is scanned, so it measures the field at one point, and you can scan it over all the surface of the tube, all the section of the tube. So how do we measure, how do we generate and measure microwaves? So to do that, we use a vector network analyzer. So this instrument is very interesting. It measures how a device under test here responds to some RF radio frequency signal, okay? And the way it does it is by separating the part that is reflected by the device and the part that is transmitted by it in both directions, okay? So what you measure is called the S parameters, S here, scattering parameters, which are the reflection parameters, S11, S22, and the transmitted parameters, S21 and S12, okay? So you have two ports, port 1, port 2, and you measure this matrix, which is a matrix with 4 parameters, okay? So how do you do that? So what is interesting is that the S parameters, they are field, okay? Field means complex field. You measure amplitude and phase, okay? So you have the full information. You know that in optics, usually you use a detector, and the detector can measure only the intensity. Okay, here we can measure the phase, and the way it is done is by using a local oscillator. Okay, so that's a reference. So you have a source, an RF source, which is multiplied by the local oscillator. Okay, and you measure the different parameters A1, so A1, B1, B2, A2. Okay, as the source goes through the device. Okay, so our device will be the tube. Okay, so that's a way to use this instrument in a quite unusual way, but we use it to do physics. Okay, so from all these measurements, the vector network analyzer computes all 4 scattering parameters that describe the reflection, the transmission, and the coupling. As a function of frequency, you can vary frequency, so we will vary frequency, and we'll see how the system responds to the excitation. Okay? So again, just remember that SAB, what we measure as an amplitude and a phase. Okay, it's a complex number. Okay. So that's typically what we measure at the output. So you see the output of the tube here. Okay, so we scan the antenna point by point, and we measure as function of frequency. So for one particular frequency, that's the typical image that you get. So you recognize the speckle pattern, okay, like with big spot, because we are in a microwave regime. So this is typically 1 centimeter, corresponding to the wavelength of the microwave of the RF signal. Okay. This is for one polarization. You can rotate the antenna by 90 degrees and do the same scan and measure the same pattern, but for the other polarization. So you have possibility to measure 2 polarization and map the field at the output. So this is the intensity of the field. Here, this is the phase. Okay, so this is a very unusual picture it's a phase representation of the phase of the field. So I don't know if you see it well, but it's represented by arrows, small arrows, and the angle, the phase angle, okay, is the angle of the arrow, okay. So I think it's very interesting because you see how the phase somehow rotates around points here. There are some positions where the phase seems to rotate. There are like domains also. There are like fractures, like in the middle, like from materials. So it's a very interesting picture that we are going to discuss. Okay. So actually, where the phase rotates by a factor 2 pi, okay. So you see it very well here. You see the rotation of the phase. So here there is a point which is a singularity. That's a singularity of the phase. So you can see that as a topological defect. Okay, it's like a vortex, you know, like a vortex when you have a fluid that turns. Okay, so those points they correspond actually to a zero of the intensity. So you can pinpoint the position where you have these vortices. Okay. And what you see is that they correspond to a zero of the field. So they correspond to a dark region on this picture. Okay, and that's a very interesting characteristic of the speckle. We always see the speckle as this figure, but this is a new representation of the speckle here that we have been exploring. Okay, so that's for one polarization. You can plot it. For the speckle for two polarization, you see that you get completely different images. Okay, so two different speckles, completely independent one from the other. Okay, it's like two different channels. I mean, each polarization is like a different configuration. Okay. So you can define the polarization. Okay, so if you define the polarization here as the angle here of this vector, which is the sum of the two polarizations, the two components. Okay, so depending on the intensity for each of the components, you can define an ellipse. Okay, which represent, if you want, the elasticity of the field, and you can plot it like that. Okay, so you can replace these two images by one image here, which show you. I don't know if you see it well. So it's like small ellipses. Okay, which tells you actually the polarization of the field. And again, you have this effect of turning a turning image around some specific points. Okay. So I can show you a zoom. Actually, we can zoom on this image here. So you see. So here we have mostly equal polarization. Okay. And you see this rotation around one point. So here you have zero of the intensity, very small value of the intensity at that point. Okay. Okay, so let's ask the question: is this speckle pattern? Does this speckle pattern follow Gaussian statistics? Okay. I don't think you are not with me in the back. No, be with me. It's interesting, I think, to follow it, to see the image. If you don't look at the image, you just completely miss the course. Just don't come if you don't want to follow it. So the question is, I have a speckle measured in this experiment. I would like to know if this speckle has a Gaussian statistics or not. So what do? I can measure, for instance, the statistic of the intensity. Okay, and what do I get? I get a very nice exponential decay. Okay, so I find the function given by the model, the statistical model. So I seem to confirm that we have this type of Gaussian variable. So circular complex Gaussian random variable. Let's look at the field itself. So that's all what we can find. We can find that the intensity as an exponential, decreasing exponential distribution. If you measure the correlation function, you will find the Sigurd relation. I'm not showing that here. I will show you later. So the correlation of the intensity is equal to the modulus square of the correlation of the field. So we have the Sigurd correlation. Again, that means short range correlation. Speckled spots are statistically independent, and the pattern is self-averaging. So that's typical of the Gaussian distribution. Let me show you. Okay, so I mean, don't miss this movie. Is really just amazing. Is it this one, by the way? Yes. Okay, so I'm going to show you here. So that this figure is for one frequency. Okay, so let's vary the frequency. Okay, and see how the speckle evolves with frequency. Okay. Then I will show you on the same picture. You will see different things. I will explain along the movie, and we'll look at it after that again. Okay, so what you see is the evolution of the speckle as the frequency increases here. So what I represent here in this figure now, I added those lines. So they correspond. Remember that we have the amplitude or the intensity, and we have the phase. Okay. So the phase is amplitude and phase can be also cosine and sine. Okay, so the line that I represent here corresponds to a 0 of the cosine and a 0 of the sine of the phase. Okay, so cosine phi has a 0 along, let's say, the red lines, and sine phi has a 0 along the yellow lines. Okay, but you cannot have cosine and sine be 0 at the same time. That's at the same position. That's not possible, right? Unless the amplitude in front of it, A cosine phi and A sine phi, unless A is 0. Okay, so when they cross here, they cross because actually the amplitude is 0, the field is 0. Okay, so that corresponds to the singularity, the vortices that I mentioned to you before. So let's continue. So you see the evolution with frequency of those lines. So you can pinpoint the crossing of these lines. That's done. Okay, so that's only the lines. Okay. I remove the speckle pattern. Then you can pinpoint the crossing with these dots here. Okay. You see how they look like they are dancing around. Okay. Then we can remove those lines and look only at those dots. And it's funny, you see how they appear and disappear in pairs. Okay, you see pairs like that, they just meet and disappear. Okay, so why is that? Because you have some singularity, the rotation is in one direction, some other singularities, the circulation is in the other direction. When they meet, they just cancel out. So you have like positive and negative singularities. When they meet, they just disappear. Okay, so they disappear and they appear also by pairs. I continue. So now you see them back inside the speckle pattern, and you see how they are positioned in the dark region of the speckle pattern. Okay, so all those parameters that are completely connected with each other. Okay. Okay, that's the phase itself. So you see actually how the phase turns, rotates, and circulates around those dots. And when they disappear, they just cancel the zeros, the rotation. Okay, so it's very interesting because those are aspects of the speckle that are never discussed and never explored, and I think this movie is really beautiful to explain what's going on. You want me to put it again? It was a bit too fast. I put it again? Yeah? So then I will not stop it, I will just let you look at it. So see how the changes of the speckle pattern are relatively smooth, okay? It's a smooth change. But after some delta nu, you see that the speckle pattern has completely changed. Okay, that's the correlation, the correlation frequency of the speckle. So that's the real part, the zero of the real and imaginary part. At the intersection, you have zero of the field, actually. Yeah, so that's probably the most interesting part of it, where you see these singularities appearing and disappearing in pairs. So you see them inside the speckle pattern, how they evolve in the dark region of the speckle pattern. And this with the phase, you see where they evolve, where you have a circulation of the phase around those singularities. So this way you can actually, exploring the statistic of the speckle, we consider the intensity, the amplitude, the intensity, okay? But you see that there are other parameters that you can consider. I will show you some example of the statistics of those singularities. You can also define and ask the question: what is the model for the statistics of these? How fast they move, how fast they appear and disappear. I mean, you can define many new parameters to describe the speckle in this way. Okay. Here, speckle evolution of the polarization. Okay, let's see what I mean by that. Okay, so that's the same. No, I think. Yeah, I don't think that's not the correct. That's not the movie I wanted to show. Probably. That's not correct. Okay, so that we saw already. Okay. So all what we discussed until now was the speckle pattern for one configuration, one frequency. Okay. You can analyze the speckle pattern and show that you have Gaussian statistics. Okay. Now we are going to step further, and we are going to consider a statistical ensemble of speckle patterns. Okay, not only one, but we are going to consider an ensemble average. Okay, and we ask again the question: do we have a Gaussian statistics in that case? Okay, so we can vary different parameters. We can vary the configuration of the disordered system. We can vary the frequency as we did before. We can vary the time. For instance, if you launch a pulse inside the system, you can look as function of time. You can also vary the polarization, the input or output polarization. There are many parameters that you can vary. Okay, and then we see that the statistic will depart from the Gaussian statistics. That's what I wanted to show you. When you consider the evolution of the speckle with some parameter, you see that actually the statistics is not anymore Gaussian. And the first proof for that is the distribution of the intensity. So if you look at the distribution of the intensity, what you find actually is that when you average over many configurations, the statistic is not anymore exponential, okay, but the statistic becomes straight. It's called a stretched exponential, okay, and that tells you that the diffusion is anomalous. Okay, we don't have anymore the statistic of the Gaussian variable. We have something different, okay, and that's what we are going to analyze further. Okay, why do we have this departure from the regular exponential decay? Okay. So let's look at the correlation function. Let's see if the Siebert relation is fulfilled or not. So you have here the field-field correlation function. Okay, so for the let's vary the for instance the frequency. So that's the field-field spectral correlation function. So we measure the average of the product in nu, P of nu plus delta nu. Okay, and this is what you obtain here. So you have the real part here. Okay, the imaginary part which starts from 0 here. Okay, so it's a complex quantity. Okay, there is a theoretical fit here which works well. Okay, so that gives you the field-field correlation function. And what is interesting is that what is called the correlation frequency, okay, which is the frequency after which we completely decorrelate the speckle. Okay, you remember the speckle changes with frequency. At some delta nu, you don't recognize the initial speckle pattern. You decorrelate completely the speckle. Okay, so this is called the correlation frequency, and it is given by d, the diffusion coefficient, over L square, which is the length of the sample. So if you measure on one point, you see sometimes bright light, sometimes dark light, sometimes bright light. Okay, these changes here are typically on a scale which is delta nu, the correlation frequency. Okay, so that gives you the range beyond which you completely lose the speckle pattern. Okay. So that's the expression, so that's the theoretical expression for the field-field correlation function. I'm not going to go deep into that and to demonstrate anything here, but what I want to show you now is we want to compare the modulus square of the field-field correlation with the intensity correlation function, okay, and see if we fulfill the Sigurd relation or not. So here, in blue you have the modulus square of the field correlation functions, so what I showed you before. So this function here, real part and imaginary part, if you take the modulus square, you get the blue line here with a quick decorrelation of the field. Okay, and if you measure the correlation function of the intensity, okay, so that's will be a measurement here, you find a function which does not overlap with the blue line. Okay, so the Sigurd relation is not fulfilled anymore. Okay, we don't have equality between Ci and modulus square of Ce here. Okay, and you see actually that first the function here, the intensity correlation function begins at higher value than 1. Okay, first, and also it decays but does not reach 0 as fast as the field correlation function. Okay, so Ci is different from Ce squared. Okay, actually you can fit the missing part here by subtracting the two curves, and you obtain here this red curve here, which is called the C2 term. So the C2 term is the long range correlation, and it tells you actually that the correlation of the intensity don't go to 0 rapidly. There is a long range correlation. That means that the correlation still persists beyond the delta nu, the correlation frequency. Okay, so you can write that the correlation of the intensity is equal to the modulus square of the field-field correlation function plus an extra function here, C2, which is called the long-range correlation. Okay, so the first term here is called the C1, is called the short-range correlation, and the C2 term is called the long-range correlation function. Okay, you understand the concept of long range? You see that this function does not go to 0 immediately. Okay, so we preserve correlation beyond the delta nu, the correlation frequency. Okay. So here I give, just for reference, I give you the expression for the C1 and for the C2. You can actually get an analytic expression for the C2 term. Okay. I put the parameters here so you know we can understand the equation. I'm not going to detail that. Okay, so that was the field correlation function with frequency, spectral field correlation function. Let's look now at the spatial correlation functions. Okay, so instead of varying the frequency, I just vary the position. Okay, so you see that the correlation length here is the size of a speckled spot. Okay, so the question is that if those speckled spots are independent, there should be no long-range correlation. Okay, so let's see what happens if we average over configuration. So here I plot again the real part of the correlation function of the field as a function of delta R. Okay, so I measure at one point, and then I compare at a second point with the delta R distance that increases. Okay, and as this distance increases, you see you have a rapid decay. Okay, an oscillation here. Typically, this is a sinc function. Okay, so that's a sinc function that describes well. So it's not exactly it. So it's a sinc function here times an exponential decay, but mostly the main term is here. Okay. So as you cross the zero line here, that's typically the size of the grain of the speckled spot. Okay. Correlation length delta R is the size of the speckled spot. So that's the field correlation function. So let's see again if the Siegert correlation is maintained or not. Okay. So let's measure now the intensity correlation function, right? So in red here you have the intensity correlation function, and you see it doesn't go to zero. Okay. If we had Gaussian statistics, these two curves should superimpose. They should be identical. Okay, but you see actually that the red one is higher, and you see that actually it goes very far. The correlation is non-zero, much further away than a speckled spot. So actually, many speckled spots, they still preserve some correlation between them. Okay. So when you look at the speckled pattern and vary average over configuration, okay, what you discover is actually that there is a long-range correlation effect. So you can write it like that. Ci, so the intensity correlation function, is the modulus square of the field correlation function here, plus the correction here, which is some coefficient kappa here, times 1 plus f. F is the field correlation function. So this is something that we demonstrated. Okay. And this is the first evidence that a speckled pattern in a disordered system actually is not a Gaussian statistics. Doesn't have Gaussian statistics. They are not speckled patterns are not independent from each other. Okay. So you understand well here. I want to make sure that you understand I am clear. It means that two speckled patterns separated by 5 centimeters, okay, very far from each other, they are correlated. Okay, if one has higher intensity, the other one should have also a higher intensity. There is a strong correlation between them. So we are completely off the standard statistics of Gaussian variables. Okay. So I want to show you in this movie how you can actually see this long-range effect. Okay, the fact that actually the speckle is not self-averaging. So again, we are going to vary the frequency here. Okay, and as the frequency vary, we will observe here the measurement at one position. Okay, so at one position we see high intensity, low intensity, so big fluctuations. Okay. Now, if I integrate over all the output of the sample, okay, if the speckle pattern is self-averaging, I should smooth completely the fluctuations, okay, and you'll see that this is not the case. So this is the measurement of the total transmission. Total transmission means integrating over all the surface here, and we'll see if we have self-averaging or not. Okay. So as the frequency varies, so intensity at one point, you see this huge fluctuation. Okay, sometimes constructive interference, sometimes destructive interference. Okay, that's for one point. But if you look at the total transmission, the integrated picture, you see also very strong fluctuations. Okay, so you see that the speckled pattern does not average out in that case. Okay, so that's what I want to show you here, the large fluctuation of the total transmission. And this is when actually we are starting to feel the effect of localization in a sample. So here I compare the two polarization, okay, horizontal and vertical polarization. So you see here that the fluctuation can be completely independent from each other, okay. But you see for the total transmission actually that there is a strong correlation between the two polarization, okay. They fluctuate more or less together, okay, and they strongly fluctuate here. And by the way, you have to stop me to make a break. So we stop here. We make a small break. Okay. To show you, so that what I showed you before is spectral correlation, right? Can I change this slide? Okay, let me close it. Start it again. Okay, so I show you that looking at the field and the total field, total transmission, I show you that the speckled pattern, so as a function of frequency, you see that actually the fluctuation with frequency are not self-averaging the speckled pattern. I just want to show you Another parameter you can change, instead of changing the frequency, you can change the time also. Okay. So the way we do that is simply by Fourier transforming the signal of a frequency into time. So let's say I take my tube with my disordered system, and I launch a pulse inside the system. On one side, I launch a pulse, and I measure the output. So what do you expect? I launch a very short pulse like that. What should I see on the other side? So some photons will go quite fast through the system. Some will be delayed more and more. Okay. So you will have actually this picture will stretch over time. Okay, over a very long time, because some photon will spend more time inside the system, and you get a full distribution of the time of flight of the photons within the system. Okay, so from a short pulse like that at the input, you get at the output like a long stretch signal. Okay, you know, it's like when you have an earthquake. Okay. So actually there is a center of the earthquake, so there is a pulse somewhere, but what you hear, what you measure actually at some distance is the earthquake itself and many replicas. Okay, so the replica actually are just scattered waves that come later in time because they have been scattered by other part of the earth. That's what you measure. So you measure a very long signal after an earthquake, so you can have replica of the event with decreasing intensity actually. So that's what we are going to see here. So I launch a pulse. I measure at one point this line here, and that line I integrate over all the system here. Okay. So what you see here, this is noise. Okay. At the beginning, nothing cross the tube. Okay. You are starting from one side, so you have to wait for the light to cross the tube. So it's noise. One polarization, the other polarization here. Okay, so let's start this movie. So you see here, so nothing at the beginning, so we launch the pulse. And then you start to see something transmitted. Okay, so polarization, they behave completely differently. Okay, and sometimes what you get at the output, sometimes you get a maximum, sometimes a minimum, so you get all this fluctuation. And as the pulse goes through, you see actually the photons that takes more and more time to cross the system, and all the thing decays over time to zero. At some point, you go back to the noise level. And what you see in the total transmission, actually, you see globally the pulse that has been stretched in time, okay, because of multiple scattering. So this is a semi-log representation, so you see actually an exponential decay of the tail of the pulse transmitted through the scattering medium. Okay, so you see actually that you have also here quite huge fluctuation of the total transmission. Okay, so if you look at the correlation function, okay, so you can actually, so that was measured actually. We measured the. So what do we have here? So this I of t. Oh, sorry. So this is actually the distribution of the intensity at one frequency. Okay, distribution at one frequency of the intensity. As a function of time, so you have an exponential decay. So that's what I showed before. So what we also here we have the real part of the field correlation function modulus square. Okay, so this is not modulus. This is just the real part. Okay, so this is this function here. Okay, and this is the correlation of the intensity here. Okay, for different parameter kappa here, which correspond to different degree of disorder. Okay, and you see compared to this black line here, which is the modulus square. I mean, this is the modulus square of this function here. Okay, So it's not FE, there is a mistake here. Okay, and you see that the correlation function of the intensity does not start at 1. Actually, it can start at higher values depending on this coefficient kappa here, which describes the disorder in the system. And you see that there is a long-range correlation. Okay, so the correlation of the intensity is not equal to the modulus square of the correlation of the field. It writes like that. So C. So this is actually a very complex correlation function. It has two parameters, time and distance. Okay, so C of t delta r is f of delta r plus this coefficient here, which depends on time times 1 plus f, where f is the field correlation function modulus square. Okay, so there is a that's a short-term correlation, and that's a long-term correlation. Okay, that tells you that several speckles at large distance from each other are strongly correlated. So that's another parameter. You can change also the polarization. That was done also in this experiment. So you have a source, you have a detector, and you can rotate the source relative to the detector. Okay, so you have delta theta s, so that's how much you rotate the source, and delta theta d, how much you rotate the detection. Okay, so actually the field correlation function is very easy to calculate because it's just a cosine of the angle. Okay, as you go from 0 to pi over 2, you completely decorrelate, and there is no relation between the two polarization. So the field correlation function is simply a cosine of delta s, and you can write the intensity correlation function, which is written here, and you find actually that you have a first term here, which is the short range, and the long range correlation term here, plus the third term here, A3, which is called the infinite correlation in the system. Is something that we'll discuss later. Okay. Just to show you that you can actually analyze the speckle from different point of view. You can look at the frequency, you can look at the polarization, the time. So you see here. Again, you see this picture here, where when you take delta theta source equal to 0, okay, so you can see that the field correlation function and the intensity correlation function are quite different. C and F. Okay, so just to give you an overview of what was done on this experiment. Okay, so we change different parameters. You can change the design. By the way, I forgot to tell you that all the idea of putting the scatter in the tube, I completely forget to tell you that, is that you can rotate the tube. When you rotate the tube, you just mix the ball differently, and you get a new configuration of the disorder. Okay, so that's the idea of this experiment, is to be able to change configuration, disorder configuration. Okay. So when you do that, we observe a departure from the Gaussian statistics. Okay. Remember, we found the stretch exponential. We don't have anymore the decaying exponential, but the stretch exponential for the distribution of the intensity. The Sigurd relation is not fulfilled anymore. We show that we have long-range spectral correlation, long-range spatial correlation, long-range time correlation also, and we have a speckle pattern that is not actually self-averaging. Okay. So let's finish that part and let's conclude on that part. So what I wanted to show you here was that looking at the speckle pattern, analyzing the statistic of the speckle pattern tells you about the interaction of light with the medium, and tells you about how the transport is modified in the system, especially when you are in the multiple scattering regime. Okay, so we have seen that we can find actually non-Gaussian speckle statistics. Okay, so if we have non-Gaussian speckle statistics, that means that one of the hypotheses that we made was wrong. Okay, essentially the wrong hypothesis is that the amplitude and phases are statistically independent. Okay, so you have two trajectories of scattered waves inside the system. Okay, they interfere at the output. Okay, you cannot say that their amplitude and their phase are statistically independent. Okay, somehow they shared part of their history as they propagate through the system. It's like they know each other. Okay, so they are not uncorrelated. They are not statistically independent. Okay, and probably that's the reason that we don't have a Gaussian speckle statistic, but a non-Gaussian speckle statistics. This can be preserved, this can be preserved. Just the first hypothesis is probably the one to remove. So that means that the trajectories inside the scattering medium are not statistically independent. Okay, so if you imagine that wave propagates, let's imagine two trajectories inside the system. Let's say that at some point they share the same path. Okay, they go through the same scatterers and then they separate, and then you measure their interference at the output. Okay, if they share some of their history, some of their trajectory inside the system, that means that they must be correlated. They have something that they share together. Okay, and that can explain the fact that because they are not fully independent, they have something in common together. That can explain the fact that the speckle statistic is not Gaussian. The hypothesis is wrong. Okay, so that translates into long-range correlation at the output. So even if the two waves share some of their paths and they create like two different speckle patterns, because they have some part of their history that they share together, these two speckle patterns will also have some correlation between them. Okay, so it's like in life, you know. You meet some people during your life and then you forgot them. Okay, I try to push. I'm not sure where I'm going here with the analogy. So you meet during the studies. You meet someone. Okay, so you share part of your life with this person. Okay, so it's possible that at the end there will be some correlation between you and that person, even if you forgot. I mean, you just lose contact with that person. It's possible that maybe you will have the same job, or maybe you will, I don't know, you will grow your children with some same approach. I don't know, because you share part of your history also. So there must be some correlation between your life, even if they look very different from each other. Okay, the analogy is like that. Not perfect, but okay. But that's what we call mesoscopic effects. Okay. So this is really there is a lot of literature on this topic. I put here a number of papers related to what I discussed with you. Okay, so until now we didn't talk about localization, strong scattering, but the fact that the system is as multiple scattering already introduced this effect of long-range correlation. But now I really want to push the story when we get closer to the localization effect. So this effect, if you remember, localization related to the fact that light is being trapped by the disorder. It cannot progress inside the system. Okay, so this is an extreme effect of multiple scattering, and actually we can observe this effect of localization, or we can be close to it. And I want to show you that the story of the speckle becomes completely different, and this is very exciting. So I want to show you here what happened to the speckle pattern. Again, we are going to vary the frequency, okay? And you can watch here the evolution of the speckle as we get closer and closer to the localized regime. I think I have something before that. Yes, sorry. First, let me describe to you the sample. I just inverted some slides. Okay, so the next slide actually here. Okay, that's the new sample that we are considering. So you remember it was like polystyrene, like plastic balls that we used before. Okay. So here we are going to use another type of balls. Actually, the scatterer is here. This alumina. Alumina is a very high index material and is 3.14 compared to 1.4 before. Okay, so very strong scatterer. So the index contrast between air and alumina is very high. Okay, and those spheres, they are put inside these styrofoam balls. They are larger balls. Okay. So you see actually there is a small window here. We put the small sphere, alumina sphere, inside these styrofoam balls. This is done to avoid too high density. Okay, we play actually on the density of scatterers by putting them away from each other. So the styrofoam doesn't influence the scattering. Okay, it's completely transparent for microwave. Okay, but the small balls here, they are very, very strong scatterers. Okay, and if you look at one ball like that, and you look at the scattering by one ball, you see that. So this, for instance, the transmission intensity. You see that there is a very strong. Oh wait, sorry. So this is actually for the. This is not for one ball. This is for the system here. When you look at the transmission of this system, okay, the disorder system, you see that there are some frequencies where the intensity is extremely low. Okay, here. This corresponds to a resonance of the alumina spheres. Okay, you remember the Mir resonances. Okay, so for this scatterer you have several Mir resonances. Okay, Mir resonance means that the energy is trapped inside the ball, and it stays for some time before being released. Okay, so the effect, the interaction between the light and the scatterer is huge. It's very strong. Okay, especially because the index contrast is very high. Yeah, you remember this figure of the Mir resonance where you see as function of frequency, you see this oscillation like that. Remember? Okay, so that's what you see. So for different resonance of the scatterer, you get, if you look now at the full sample, you get very, very strong scattering. Okay, and very little of the light is transmitted through the tube. Okay, this is a log scale. Okay, so this is very, very small. The light almost cannot go through the tube. Okay, so that's what I wanted to show you. It's a different sample, and this is a sample where we are reaching the regime of localization. So I want to go back here and to show you how the speckle pattern will evolve. So we are going to, what is the frequency? 9.5. So if you look here, sorry, if you look here, we are going to go from 9.5 somewhere here, okay, and we are going to cross this region here, okay. So we go from a region where we have transmission to region where the transmission is very low, okay, and we are very close to the localized regime here, okay. So look at how the speckle pattern changed. Remember how it was changing before, okay. So look now at the difference here. Wait, we do that. Okay. So you see the speckle pattern changing quite smoothly with frequency. You see also the singularities here. And then we are getting closer and closer to region where the transmission is very low. Okay. So and then you see the evolution of the speckle just completely change. Okay, it gets like frozen for some time, and then change to a new image, a new pattern. Okay, so you see the correlation are very strong with frequency, because you maintain the pattern for some time here, some frequency range. Okay, and it's just jumping from one pattern to another pattern. So we don't have anymore this smooth change of the speckle pattern as we used to have before, but we have this completely different behavior. So if you look at the beginning, yes, you have this change which is relatively smooth. Okay, and when you reach a regime where small intensity here, then you see also the singularity. They get like frozen for some time and then change brutally to other values. Okay. If we just put my so that won't run out of battery. Okay, so now you understand that clearly the speckle pattern doesn't behave in a normal way. Okay? It is completely anomalous, completely different. Okay, so let's try to understand what's going on here. So when you look at the speckle pattern for one fixed value of the frequency, okay, actually you don't see any strong difference between a diffusive speckle pattern and a localized speckle pattern. Localized, I mean in the regime of localization. Here in the regime of diffusion, okay, they look about the same. Okay, the intensity is much weaker here. The measurement is much noisy. Why? Because transmission is very low. Okay, so it's very hard actually to measure this type of speckle, but the distribution is about the same, right? I must say that this is normalized. I mean, the color scale is normalized to 1, but actually the intensity is much lower there than here. Okay, so here we are at 9.5 gigahertz in the diffusive regime. Here 10.4 in the localized regime, but they look really the same. Okay? Now, if you look at the spectrum, okay, as a function of frequency, okay. If you look at the intensity as a function of frequency, okay, then you see very, very different pictures. Okay, so that's the diffusive regime. So if you measure at one point, you see sometimes high intensity, sometimes low intensity. Okay, and it's a smooth variation. Okay, constructive, destructive interferences that alternate. Okay. But if you look in the localized regime, what you see, the spectrum is very, very different. Okay, so you see that actually you don't see anything, and then suddenly you have a peak here. Okay, so during this peak, the speckle pattern is frozen. It remains the same. Okay, then you jump to another peak. You have another speckle pattern. Okay, and so you see actually that. The correlation frequency here is given by the width of the peak here compared to the width here of the variation here. Okay, so you see those jumps seems to be related to the peaks that you see here. Okay, and I think we discussed that earlier in the course, that those peaks correspond to modes actually of the system. But let's go and look at again, a cooperation between diffusive and localized. How do I run this movie here? So that's the diffusive case. So here you have both the speckle pattern and the singularities, and the phase, the lines are the phase turning around the singularities. Okay. And for the localized case, you see how the pattern remains frozen when you go through a peak, and then change to another peak, so another mode, okay, where the frozen evolution of the singularities of the pattern itself. Okay, so what has been done here in research is to explore the difference in the statistics of the evolution of the singularities. Actually, you see that if you look at the way the velocity of, I mean, how they move, the velocity of those singularities, okay, in the diffusive regime is more or less there is like more or less an average velocity, okay, around which they move. But here it's like either like frozen, so very small velocity, or very fast velocities. So we said maybe we should look at the statistics of those velocities, okay. And that's the next slide here, and you see a very different behavior. So that's how much, so that's average displacement of vortices for fixed delta nu. So you change the frequency by delta nu, how much the singularity has moved. So it's the velocity actually of the singularity. So you see that for the diffusive case, you have something which is peaked around some value with more or less a symmetric distribution around that value, okay. But in the localized case, you see that you have actually very small values, so very slow displacement of the singularities, okay, that is peaked here, and then you have a long tail corresponding actually to very fast movement of the singularities. Okay, so what I want to show you here is that you can really develop a completely new description of the statistics of the speckle, and actually you can find a signature in the singularities themselves, in the distribution of the singularities. You can find a signature that differentiates between localized and diffusive regime. Okay, so that's the power of the statistical approach. Okay, even if we don't have a model to describe that, looking at the statistics can tell you actually in which regime we are. So in conclusion, okay. So just to conclude here, what I said actually from last week is that the statistic of the speckle pattern, in general, they are generic. So what do I say here? So while the statistics of static speckle pattern are generic, fluctuation in their configurational or spectral or temporal evolution are strongly enhanced in the vicinity of the localization transition. Okay, so when we get closer to localization, we start to see very strong effects that completely modify the way the speckle pattern fluctuates, evolves with different parameters, the configuration, spectral, temporal, polarization. Okay, all these fluctuations are completely modified when you are close to localization. Okay, so these actually can be used to probe the transition from diffusive to localized regime. Okay, so we have seen that we have a strong departure from Gaussian statistics. Okay, and this difference is increasing as you get closer and closer to localized regime. Anomalous statistical properties that we saw, and I wrote here that the anomalous statistics of the speckle patterns near the localization transition reflect the underlying nature of the modes which evolve from extended to localized states. So those modes that I show you in the spectrum here, okay, those peaks actually correspond to modes in the system, resonances inside the system. Okay, actually they are strongly localized in the system, and that completely modified the picture. Okay, so how do I know that they are localized? Simply because the line width is very narrow here. Okay, so if it's narrow, it means that the losses are weak. Okay, so imagine the tube. Okay, you have the tube, you have the wave coming, exciting a mode inside the system, so there is some energy that builds up inside the system and then exit from the system. If the mode is extended, okay, so the leakage out will be very strong. Okay, so the width of the mode will be large, like here. If the modes are localized, they are confined inside the system, they have very little overlap with the output of the sample, so they will be excited, they will release energy, but with a very high quality factor, very thin line width here, and that's the signature of localized mode. So that's something that I will push further in the next chapter. Okay, any question? I'm sure you have plenty of questions. No. Yeah, so what really I wanted to show you in this chapter, I'm done with this chapter on speckle pattern. Some references here. Yeah, so I think to give you like the full picture of this chapter, I wanted to show you that speckle statistics actually can be used to describe the speckle obtained by multiple scattering, by light multiply scattered in disordered system. So the model that I proposed at the beginning, which is the Gaussian statistics, does not work anymore for multiple scattering. Okay, and actually the departure from this model is stronger and stronger as you get closer and closer to localization. Okay, so that's for this chapter. I'm hesitating to move to the other chapter. Maybe that's enough for today. What do you think? I wanted to introduce you to localization, to different effects that are specific of localization. Maybe it's a good idea to keep it for next time together, right? It's okay with you? Yes? So this chapter is already on the Moodle. Maybe you are following it on the Moodle, I don't know, before. So next time we will explore what is called the regime of localization. So it's either weak localization, strong localization. We will discuss these different effects. That will be already January. We will be already in January, and we'll have I don't know if we have 2 more sessions or 3 more sessions. Maybe 3 more before the exams.
2 more.
2 or 3?
2.
Only 2?
Next week, and one after them.
Yes.
More 3 weeks.
The 19th is in 3 weeks?
Yes.
Oh wow. Okay, so let's leave it for next time, and okay, we'll adjust. Okay. So thank you. If you have any question, or if you want me to give you more explanation, or if you want to come to the lab to see the experiment, by the way, you can come. CD will introduce you to that experiment.
So can you send me that presentation? Can you send me the presentation?
I sent it to you.
No, the
No?
old one. No, I didn't receive. I thought you will send it together.
I didn't send you yesterday or 2
No,
days ago.
last 2 weeks you didn't send me.
No, I did it on maybe on Sunday or.
Send me no.
I sent it to you again anyway because